friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I will show one thermal analysis using SolidWorks. Here in this case we'll consider conduction, and by the same time it will be radiation in the form of electromagnetic radiations inside a valve. We'll analyze this one using SolidWorks Pro simulation, right? So we'll start it from simulation, and the environment of this simulation can be initiated with the wizard itself. So we'll start with the wizard. Let's select the default project name as project 17. Next, and we are considering this one as SI system, and temperature will take as degree centigrade. Next, now in this case we are considering internal analysis. We can show this one using external analysis also. That internal and external analysis based on what type of goal we are defining. So in this case we are concerned about the distribution of temperature inside this valve, including the base of the valve and also the inert gases inside this valve. We want to see the distribution of temperature inside this inert atmosphere. So we are considering internal analysis. If we are bothered about the top surface of the valve, in that case the external analysis can be done, right? So we are taking internal analysis as we are bothered about the base temperature and also the temperature of the inert gas which we have provided inside this valve, right? So it is heat conduction in solids, and as inside this valve we are providing some kind of inert gases, so it will be gas also. So we are not clicking this one. If we are considering completely vacuum inside this valve, in that case we have to click this on. That means it is completely solid, no gas will be there, no inert conditions will be there inside. But here in this case we are considering some inert atmosphere using argon and nitrogen, so we have to select some gases also inside. So uncheck this part. And radiation we are considering, and inside this valve the temperature is actually very less because we are considering completely vacuum. So temperature will be minus 270 degrees centigrade or absolute zero, right? We're considering temperature minus 273 degrees centigrade. Next, gases. Okay, we'll select argon as the main gas, and together with that we'll consider nitrogen also. Very less percentage of nitrogen will be there. We have selected argon and nitrogen. Next, alloys. The base of the valve, it will be made up of alloy steels. Let's select steels, stainless steel 321. Next, and for defining these boundary conditions, default boundary conditions we will not consider right now. We'll check it. Let's make the boundary conditions like non-radiation surfaces we are considering right now, because at the time of actual application of boundary condition we will provide as per our requirement. Now at this point we are considering non-radiating surfaces. Similarly, for default outer wall we are considering non-radiating surfaces. Next we have to select the concentration, that means how much percentage of nitrogen and argon should be there. Let's select argon to be 90%, as we are providing inert atmosphere inside this valve, so argon will be 90%, and let's select nitrogen to be 10%. Let's finish it. This is our computational domain. That means inside this one all the iterations and calculations will be taking place. More the volume of this one, more will be the time for these calculations, so better to make it as small as possible. Okay, so let's hide this part. Computational domain, make it hidden. The computational domain is hidden. Now we need to apply some boundary conditions. First of all we should apply materials. So solid materials, insert solid material, predefined. We have to apply alloy steels at the base of the valve. So let's select that alloy. it is stainless steel 321, and that to be applied at the bottom of this valve. So let's select that one, valve inside part, that is the bottom one, right? This one already selected. Actually the model we have taken into 3 different parts: the base part, this filament part, and the top part. We have taken this valve into 3 different parts and assembled together. The base part is made up of stainless steel, and this filament is made up of tungsten, and the top part is made up of glass. It is transparent glass. Okay, so the base part is provided with stainless steel. Green check. Next one, you have to provide that filament. So again, solid materials, insert solid material, predefined, and we have to select the material. It will come from metals, and it is tungsten. So you have to select that part from here, tungsten filament you are selecting. Green check. So material is already provided. Next one, we have to provide glass for the top part of this valve. Solid materials, insert solid material, predefined, glasses and minerals. You have to select glass, and the top part of this valve we have to select, and it is transparent, so we have to select transparent. Green check. So all the materials have been provided. Next one, for lighting, what we have to do is we can provide heater at this filament, or we can provide a specific temperature on that one, right? Let's provide a specific temperature on that filament. So it will come from boundary conditions, insert boundary condition, and it will be walls, real walls, and we want to provide a specific temperature. Let's provide the temperature of 2000 degrees centigrade at the filament. So it will be here itself, we will provide temperature of 2000 degrees centigrade temperature at that filament. So to select that filament part, green check. So filament is provided with constant temperature of 2000 degrees centigrade. Done. Right. Next one, we have to start with our radial surfaces. Now for applying these special boundary conditions, better to cut this valve into 2 equal segments. Let's cut it from the front plane. We can cut it from the front plane. Green check. This is the valve into 2 equal segments, right? Now we have to provide that boundary conditions right now. So what we'll do is insert radiative surface, predefined, black body wall. We have to select that radiation from this filament to the inside part of this valve one. So we have to select the filament, tungsten filament, and the inside part of the valve. So from here to here, radiation will be there, right? It will be in the form of electromagnetic waves. Green check. Next one, the bottom part of this valve, that is the base part, will be acting as a reflecting surface. The base part of this valve will be acting as a reflector. So we start with radiative surfaces, insert radiative surface, predefined, and it will be acting as a reflector. So we can select wide body wall. Green check. All the boundary conditions have been applied properly. Next we can select some goals. So you can select the complete view of the model. Now goals, insert surface goals. We want to have some goals like temperature of fluid, temperature of solid, and the temperature of the base of this bulb. We can check it. So we'll select average temperature of solid. Select average temperature of solid for the base of this one. Green check. Let's cut this one. It's better to select the proper sections. We can rename this one as average temperature of base of valve. Now another goal we can select, goals, insert surface goal, we have to have the temperature of the inside surface of this bulb. So select that location, and it will be temperature of solid and fluid, both we can select. Let's select temperature of fluid and solid separately. Initially we are taking temperature of solid at that surface, average temperature of solid, green check. So we can define this one as average temperature of bulb inner surface. Another goal is required, that is we want to have the temperature of fluid inside this bulb. Insert surface goals. It will be temperature of fluid, average temperature of fluid inside this bulb, we want to see. Green check. So all the three different goals we have defined. Next we can run this simulation. So let's run it. We can start new calculations. The iterations have already started. The iterations are going on. It will take some time for completing these iterations. Whenever it is finished, we'll see our results and analyze it. Okay. We want to see our results in the form of cut plots. First one, we'll see the cut plots in the form of temperature of solids. Let's see it from the front plane. This is the cut plots. It is better to understand these things in the form of an animation. Let's see the cut plot and play it. It is showing the temperature of solid across the front plane. It will be better to see the temperature of fluid. Let's change it to fluid, because inside we have provided a mixture of argon and nitrogen. This is temperature distribution of inert gas atmosphere inside this bulb. We have mixed 10% of nitrogen together with 90% of argon gas. Okay. And it is clearly understood that at the base, where the tungsten filament is inserted, it is having higher temperature and it is completely solid. So the temperature actually at this range it is high. So conduction is occurring at this base. Let's zoom in to that part. See, the base is made up of alloy steel, and so pure conduction is going on through this base, and the temperature of that one is very high. The temperature of that one is in the range of 2000 degrees Celsius, and above it is less. Let's clear and hide this part. Next one, we'll see our surface plots. Insert. We have to see temperature of solid. And we want to see across all the faces. It is providing the same trend. Like at the base we are having alloy steels, so pure conduction is occurring at the base, and top part, by radiation heat is being transferred along the top circumference of this bulb by the way of electromagnetic wave in the form of radiation. And bottom side we are having solid alloy steels, so we can see that conduction is there and the temperature of this place is very high, in the range of 2000 degrees centigrade. As the filament is inserted inside this base plate, so pure conduction is occurring, and that's why the temperature of this base is very high. Right? Now we have to see our goals from goal plots. insert goal plot. Let's see the goals. You can see the average temperature of base, which is made up of alloy steels, is in the range of 1892.6 degrees centigrade, and that of the valve top surface is 899.64 degrees centigrade. Okay, we can see these things in the form of a graph also. Let's see in the form of history. It will be easier to understand this one. So initial temperature was minus 273 degrees centigrade. So temperature of the base was minus 273.15 degrees centigrade, and after 720 numbers of iterations, we can see the final temperature of the base is in the range of 750 degrees centigrade approximately. Right, you can see here it is approximately in the range of, here it is 750 degrees centigrade approximately. Similarly, the temperature of the fluid, initially it was in the range of minus 70 degrees centigrade approximately, and then after near about 620 numbers of iterations, we got the final result to be 926.85 degrees centigrade. Okay, so this is all about our today's analysis of electromagnetic radiation inside the valve using SolidWorks. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.